Our next speaker is going to be Malena Sabaté Landman, and she's going to be talking about motion correction for cardiac MRI images using generative neural networks with disentangled latent space variables. Malena.
Thank you. Not that one.
No.
I've already seen this one. I can repeat it.
You can just you can do it again.
Okay, so yeah, I'm going to be talking about generally just trying to solve linear inverse problems of that form. So we assume that we know the linear operator and we have some additive Gaussian noise and want to recover the solution X. And in particular, I focus on an example on an MRI. So of course, it's have a substantial Fourier transformation of over some core sensitivities, but this is a general framework that can be applied with more generality. Because we have a nil post problem, we need to add regularization, which means that if we just solve the problem, we'll probably just get rubbish, basically. And because it's a very high dimensional problem, we need to use something like an iterative package. So in the classical variational regularization setting, we'll have something like the thing on the top. And in particular, I wanted to focus on thinking about this X, or this solution being in the range of a generator. And in particular, I want this generator to incorporate in some way prior information about the solution. And this is somehow similar to having a projection method where you have a dictionary or like some sort of linear transformation, and then you can have this parallelism between regularizing or enforcing some properties on the solution by penalizing or enforcing some properties on the projected space or on the coefficient. And how I'm going to do this in this setting, well, what I want to do is to give some structure to the latent space. So I actually want to divide this latent space into different components, and I want each of these components to be related to something that I already know or I assume will happen in the solution space. So instead of penalizing or enforcing properties on the solution, I'll enforce these properties on the latent space. And in particular, I'll be applying this to full motion separation. So I have each frame of the video being the output of the generator, and now you'll see that the latent space is split into different components. And the only thing I want you to focus on is that we have a Z1 and a Z2 that both depend on time. And I'll explain you how these will have different, will be related to some properties of the video at the end. And in particular, we also don't train, so I will not use any other data than just one measured video. And I'll minimize over all the parameters. So I'll minimize over the parameters of the network, but also on the parameters of the latent space. And to make things easier, and that it's not necessary in all cases, but to make things easier, I'll assume that I have some prior 1D information about one kind of the movement. So for example, I'll be talking about, or the examples we have are on dynamic MRI data. So we have a heart beating, and we'll have some information about the motion of the heartbeat or the breathing. So the data we had, you've seen this data before, is that a heart beating. So we concatenate with 3 different heartbeats, and we added on top some fake breathing motion. So we have this like mixed breathing and cardiac motion in the data. And then we reconstruct this full video using this specific technique. And what we want to do is that each of the like Z1 and Z2 of the latent space will either correspond to the motion or the state of the heartbeat motion or the state of the breathing motion. And here you just see the red line, which is following as we move horizontally on the picture on the bottom over time. So on the right, you see the exact ground truth solution. So you see there's like 2 breathing cycles and 3 heartbeat cycles, and you can see in the second and third row. And we have the reconstructions in the middle, which look quite good. And again, you just obtain them by fixing one of these parameters in the latent space and moving the other one, and vice versa. And you have some upscaled version of the error on the right. And it's just another example to say that, you know, these things work well with some generality. And you can also recover some physically meaningful information about this movement in 1D just by looking at what is the reconstructed output, reconstructed input in the latent space. So just to summarize, I think is really interesting about this project that we like mixing untrained generators and latent space entanglement. and we can use that for full motion separation and not just motion correction. And I think it's quite interesting because it doesn't need training data, so it doesn't have data bias. And it's quite good for extrapolation to unseen combinations of breathing, and our heart data could just be used in completely different kinds of motion. Thank you.
Our next presentation is going to be by Carlos Esteva Gagwe. Thank you.